Namaskar. Today we will discuss energy function in configuration space and Jacobi integral and some other results related to energy function in configuration space. Actually, as I told you earlier that there is a way to solve the mechanical problems, which is the known as Newtonian mechanics. There is another way in which we use the Lagrangian mechanics, where Lagrangian function or simply the Lagrange's function, known as Lagrangian and denoted by capital L, is introduced. And this function is introduced in configuration space. So in this lecture, we will discuss about the energy function which is introduced in configuration space under certain conditions. If we talk about the conditions, we'll consider suppose three conditions. Number one, we are having one condition that Lagrangian does not depend upon time explicitly. This may be the one situation. Second condition is that system is conservative. That is, there exists scalar potential function V, standard notation, independent of generalized velocity. And there may be one more condition that transformation equations do not involve time, or these are independent of time. What are these transformation equations? These are from conventional coordinate to generalized coordinates. So if your system of particle is represented by Ri, positions Ri, then this Ri is a function of Qj and as well as time. So under third condition, there will be no dependency on time, where Qj are generalized coordinates. So this is the initial description or the transformation equations for your dynamical system. Now, first of all, what is our Lagrangian? Lagrangian is defined as function of Qj, Qj dot and time. From this L, you may find what is your time derivative of Lagrangian, total time derivative of Lagrangian. Naturally, you will differentiate Lagrangian partially with respect to Qj and then Qj with respect to time, then Lagrangian with respect to Qj dot, and then Qj dot with respect to time, and partially you will differentiate L Lagrangian with respect to time. Now what is Lagrangian equation of motion? Lagrange's equation of motion is Here I have not put the summation symbols, while this is summation with respect to G. This is derivative of delta L delta Qj dot minus delta L delta Qj is 0, or Qj is delta L delta Qj. So we will use this relation 3 in relation 2. So relation 2 implies dl dt is equal to summation. In place of this delta L delta Qj, I'll put d dt of delta L delta Qj dot, then dQj dt plus summation delta L delta Qj dot, and I may write it as derivative of dQj dt, because you are having here Qj dot. This is Qj dot, derivative of Qj dot. Now combine these two terms and write it as delta L delta Qj dot dQj dt. These two terms are actually the derivative of product of two functions. Now L minus delta L delta Qj dot dQj dt is delta L delta t. I have taken this term to the left hand side, or reversely you may write it as d dt of, इसको मैं पहले लिख रही हूँ, और what is delta L delta Qj dot? It is Pj by definition, and this is Qj dot. This term is Qj dot and this term is Pj. Minus L is equal to delta L delta T. Now in this relation, if I take first condition, what is the first condition? That Lagrangian does not depend upon time explicitly. So in under first condition, this derivative will be 0. So I am considering the first condition, and the first condition is saying let condition 1 holds. Under this condition, this will be 0. If this right hand side is 0, we'll get Pj Qj dot minus L is 0, or Pj Qj dot minus L is constant. We denote this Pj Qj dot minus L as small h, and this is known as energy function. This is the energy function in the configuration space. This is very important to note, because in this case, we are defining Lagrangian. We are considering Lagrangian. Lagrangian is defined in the configuration space. So this is the energy function in configuration space, because this type of definition you will use for Hamiltonian. But that Hamiltonian will be described in some other type of space, which we will introduce later. So it is the energy function. So this implies H is equal to constant. When I write this in this form, then this is also known as first integral of motion, and you get one result that if Lagrangian does not depend upon time explicitly, energy function is constant, right? Uh, this is also known as Jacobi's integral. This 4. 5 is also known as Jacobi's integral. But existence of Jacobi's integral does not mean that your system is conservative, because I have not assumed this condition. So existence of Jacobi integral does not mean that the system is conservative. Even for non-conservative systems, your Jacobi integral will exist. This is known as first integral of motion, or the Jacobi's integral. First integral of motion. So this is one result about this energy function. Now we consider some other conditions. Suppose we consider this condition that transformation equations do not involve time. Suppose I take this one, third one. Now what will happen if condition 3 is true? This is the next part. If condition 3 is true, that means what will be delta R I delta T? This will be 0, because transformation equations are independent of time. Now, what is your kinetic energy in terms of generalized coordinate? We know the expression for kinetic energy was, in standard notation, it was written as T0, T1 and T2, where it is half mi. यहाँ पर आप समेशन ध्यान रखिएगा, ये सब आपको लगाने हैं समेशंस. This summation is for G. Yes, half mi delta Ri delta T square. Again you will put summation, then summation mi delta Ri delta T delta Ri delta Qj dot plus This summation is naturally for I and j. Then summation mi delta ri delta qj delta ri delta qk qj dot qk dot. This is an expression for kinetic energy. Now under this condition, under condition 6, this part will be 0 because here you have the partial derivative of ri with respect to time, and this part will be 0. Here again you are having derivative of ri with respect to time, so you are left with T is equal to sigma mi delta ri delta qj delta ri delta qk qj dot qk dot. So T is a quadratic function of homogeneous and quadratic function of q dot. So we will use the Euler's theorem, which says that qj dot delta T delta qj dot may be written as twice T because it is quadratic, homogeneous quadratic function of order 2. So if your f is a homogeneous function of order n, then what Euler's theorem says that you can write function order n function of x of order n. You may write x delta f delta x is equal to nf, and because it is a quadratic, that means it is of order 2. So in place of n I have written 2. So qj dot, this delta t delta qj dot is pj is twice t. Now I use the definition of energy function. It is 8. Now since H is defined as summation qj dot pj minus L, and you see when we define this H, we have not used any of the condition. So existence of H does not need any condition. Yes. So use in 8. We get H is equal to H plus L is equal to twice T. Or H is equal to twice T minus L. Now you can write L either in terms of T minus V or in terms of T minus U. It depends that whether your scalar potential function V is existing for conservative system or your U exists for non-conservative system. So now we will consider another condition, which is your condition 2. 2 says you have already taken 3 and now you are taking 2. So 2 is saying let the system be conservative. Then L is equal to T minus V. So H will be twice T minus T minus V, or it is T plus V. What is T plus V? T plus V is total energy. Now what we get? You look at the results. Number one, now you look at the results. Number one, you get H as energy function in configuration space. Number two, you find that H is equal to constant if L is not depending upon time. Number three, H is equal to T plus V if transformation equations are independent of time and system is conserved. So you see the existence of H. This is H. This existence of H requires no condition, no restriction. H is constant, H is conserved when Lagrangian is explicitly independent of time. Here H is the total energy function. So H to be the total energy function does not mean that H is conserved. Your system is conserved, but still H represents total energy is not necessary. It simply means that your situation may be like this, that H exists and is equal to total energy, but need not be conserved, right? Now if Lagrangian is not a function of time, then because H is constant, then H is total energy and is conserved. Number 3, H is constant, means H is conserved but need not to represent total energy. The reason being that it will represent total energy when your system is conserved. So these are certain consequences or results, properties regarding the energy function in the configuration space. Thank you.